So my name is Chaz Emerick. Very glad to be here. Thank you very much to the folks at Chariot and Philly ETE for setting things up and inviting me down. So I am speaking today about distributed systems and what I'm sort of going to boldly call the end of the API, hoping to slaughter a particularly sacred cow here, and we'll see how it goes. So the problems that I'm going to talk about, I don't have any turnkey solutions for yet. It's something that I've been working on for an extended period of time now, and sort of talking about it publicly and talking about the set of problems is me getting close to being able to provide some kind of turnkey solution for many sets of applications and systems that have the problems that I'll describe. What I want to do is point to some, I think we can say is consensus about a particular set of problems in distributed systems that we experience today, and some strategies that have really emerged over only the past 5 to 10 years really about actually proven ways to mitigate and resolve those issues. And one thing I want to do for just 1 minute is say why you may want to listen to me on this topic. Perhaps you may know me from the Clojure space. I've been working in and around the Clojure programming language for almost 6 years. Wrote a book for O'Reilly, and that's largely what I'm known for in programming circles. But for the past 2 years or so, I've been working essentially full-time on a particular set of distributed systems problems, and this is part of a distillation of that. So there are two claims that I'm going to make here. One is that the notion of a networked application API is really an anachronism, that it doesn't account for the necessary complexities that the nature of modern distributed systems present to us. And then secondarily, that there exists a set of formalisms that, as I said, have really come about only in the past recent history that account for those complexities and yet are entirely absent from modern programming practice. And so we'll get to see the shape of those in just a little bit. I do want to get into some definitions just because distributed systems and APIs, they're very large topics, and I'm actually talking about a subset of each potentially. So almost every system that we build today is a distributed system. And the sort of catchy, jokey phrase is that a distributed system is one in which a machine that I have no knowledge of can cause my program to fail. I'm not sure who coined that originally. I heard it first from Sean Cribbs at Basho, but it's sort of a catchphrase that people who are interested in distributed systems use to sort of drive home the point that anything that we're building today has the problems that are grouped under the umbrella of distributed systems. Sort of an informal definition is it's any system comprised of multiple processes that must communicate to perform work. And so that can be different processes locally, they could be on different machines, they could be in virtual machines, all the same sets of, all the same classes of problems apply. And what I want you to take home from this with regard to distributed systems in particular, if you're not familiar with the field as a thing, is that when you distribute a system in a networked fashion, you yield very unintuitive semantics around causality, consistency, and availability. And this has significant ramifications for how you build systems to cope with those problems. And again, if you haven't accepted that you're building one, your luck will inevitably run out. So the simplest thing of one process talking to a database is a distributed system, as well as a front-end web application that communicates with the simplest possible backend is also a distributed system. A lot of the same problems apply there as apply in the largest distributed systems that we know of today. The notion of an API is one that has been around forever from a programming perspective. It's really just the set of names that we interact with in our languages and libraries. And this has a long history going back to probably the VAX systems where they had actual libraries to work with as opposed to manipulating machine code directly. But at some point when people started hooking computers up together, they wanted to be able to reuse that same sort of language abstraction, to be able to name things and name processes, name operations, name data. And they carried along this notion of an API along to network programming and modern distributed systems. Sort of the root problem of this is that it's a strictly nominal thing. You're naming things. You're not providing any sort of specification of what the semantics of the operations you're performing have. So when you go into your nearest Java doc and it's doing some network programming, it's not going to have any specification of what this operation's semantics are in the course of a network partition, for example. And that's the simplest sort of example, but that lack of defined semantics within APIs, network APIs, leads to a lot of confusion and a lot of faults when you are building a distributed system and aren't accounting for those complexities up front. So this is a progression. It's roughly temporal in terms of the types of technologies that people have used to connect applications together in a distributed system, and it's a very rough progression, but it's basically accurate. And the notable thing about this is that they're all fundamentally equivalent. It's possible to quibble about this to a certain extent simply because things like RPC have very specific implementation details that are not shared by something like REST or SOAP APIs. However, they all share the same fundamental sets of semantics, and those derive from their programming language heritage. So when you call an API in Java, it has a particular set of semantics. It's a synchronous call. You're providing some data. Ideally, you're getting some data back, and all those semantics carried into the notion of an API when doing network programming. All of these are effectively request response. All of them are fundamentally synchronous. I know a couple of them have sort of end arounds to model asynchrony. However, they're very rarely used, and it's more of a idiom or pattern that you apply as opposed to something that is inherent within the mechanism in question. All of them presume a point-to-point communication topology, which is sort of a fatal flaw, especially given modern distributed systems, which really are not just a hub and spoke. You may have meshes, you may have hybrids between point-to-point communications and things like buses, and so all these types of technologies don't account for that. They're almost always imperative by nature, so they presume mutable data models and side-effecting operations. And if you are interested in or enthusiastic about functional programming and the immutable data models that come along with that, this should make you uncomfortable. And sort of beyond the notion of immutability, all of these mechanisms place very few constraints on the data models and representations of data that you push through them. So for example, it's just open up a socket, you're using HTTP, you can push whatever you like down the other end, and it's entirely up to you to constrain the semantics of that operation on both ends in order to yield the types of performance and application semantics that you want to guarantee. So the source of all truth sort of comes out on Twitter first, right? So this was what I tweeted when I was sort of contemplating the premise of this talk. And I pick on REST just because that's the most modern thing, but you could replace any of those other technologies there, as well as any other imperative, synchronous, point-to-point network application interface technology that you might want to look at and drop that in its place. The thing that APIs really focus on is programmer convenience. And I mean this in a very specific way, in that the focus of all of these mechanisms is to try and maintain an isomorphism between method calls that we're used to within a single process, imperative, say, programming language, and things that we do over the network. So there's a clear isomorphism between calling a local method on a local object, or calling a method on a stub for an RPC endpoint, and performing these REST or otherwise HTTP API calls. And the ironic thing is that while things like REST and other HTTP APIs are sort of touted as being better than RPC in a variety of ways, and in certain ways they are in sort of the details of their implementation, modern practice is such that vendors of these APIs or producers of these APIs very often provide things like client libraries that restore the exact problem that people were originally trying to get away from RPC, which is sort of obfuscating the fact that when you make that create call through an API, that's actually causing network calls and exposing you to all of the tricky semantics that are associated with distributed systems, but you don't know that. And so when you're in a JavaScript environment, for example, and you make a call on an object, you're not sure whether that's going to produce XML HR calls in the background. You're not sure what the semantics of that call are. And so it's still just a method to lull us into thinking that we're making just method calls locally and putting the blinders on, which is convenient and is very familiar, but doesn't address the problem space that we need to be working within. And so it's sort of like it's trying to say, there's a lot of stuff going on here. You don't need to worry about it. It's all going to be magic. We're going to send data to the server. You're going to get it back, and everything is going to be unicorns, which we all know is not the way things work in the real world. So I'm going to beat up on APIs just a little bit more to drive the point home. There's an intense coupling between the client and the server, both in terms of the point-to-point topology as well as the data model that you're using to represent the operation that you're performing. It requires this two-party client-server architecture, despite, again, the realities of other network and application topologies that are in use. And the network failure modes, sorry, my computer did something strange just now. Many network failure modes and common sorts of computation require asynchronous processing. And so we end up having to have these idioms and patterns to work around the fundamentally synchronous nature of these API mechanisms to do what we need to do. Again, APIs have nothing to say about the fundamental complexities of distributed systems. This means failure modes that are network related. This means guarantees or requirements that we need to have with regard to availability, consistency, and the data model that we're using to perform the work that we need to perform. And so I just wanted to drive this home. It's been proven that there's some limited set of network topologies. When you're building a distributed system to a large degree, you're subject to them, and sort of logically, your application has an architecture that mirrors one of these network topologies. And so APIs, as we know them today, account for just one of them, the point-to-point one. And so all these others have fantastic uses, and we do create them, but we build them out of that fundamental building block of a point-to-point architecture, and then have to accrete all this CRUD to sort of ensure the semantics that we need if we're building a bus or if we're building a gossip architecture, whatever we're doing. So, what do we need to do? We need to acknowledge the context that we're in, and the 800-pound gorilla in the room is that you're not calling a method locally in process. You don't have local data. You have a network between you and however many other actors within the broader distributed system that you're building. And so you need to acknowledge the network and acknowledge the realities of that network. Networks have a lot of different failure modes, and I'm not an expert in network engineering, and there's plenty of other people that can speak to it more authoritatively than I, but certainly there are partitions, and this could mean a complete loss of your interconnection between 2 points within an API call, either because a switch goes down or someone shuts off their Wi-Fi or whatever. You have, honest to goodness offline operations, so if you are working on an application and you want to enable offline access, currently APIs provide no notion of how to handle that. You are entirely on your own. And again, variable latency is sort of the broadest description of a partition. So a complete partition where a node goes down can be interpreted or characterized as latency as infinite latency, right? Whereas in the normal course of operating a distributed system, whatever its architecture or characteristics, your latency between each actor is going to fluctuate based on the vagaries of the network that you're operating on. Again, messages can be reordered in networks depending on the way that TCP is routed and the particular data models and API mechanisms that you're using. Messages can be repeated. These need to be accounted for both in your application semantics as well as in your data model. And so your network's problems really are your system's problems, and you need to sort of internalize that and realize that it's another party in the room. It's not just you talking to other code on the other side. There's this thing you need to account for. And if you take the broadest possible characterization of many distributed systems, your clients, the people and devices and vendors at the edges of your system, their networks are also your system's problems. And so even if you can stipulate that we're going to have 100% uptime in our data center, for example, which doesn't happen. Even if you can stipulate that, you need to still consider what's happening on the internet, what's happening with my vendors' APIs that they're providing, what's happening with the devices that my system is controlling. The network in between all of these parties is involved in defining the actual characteristics of your distributed system. So consistency sort of affects everything. And again, consistency is a huge topic. Sort of every one of these slides could be 3 talks all on its own and define careers in computer science and things like that. So we're moving pretty quickly through a lot of material. But just to give you the lay of the land, the degrees of consistency that you have within your application are dictated by the degrees of consensus that you apply. Consensus very roughly is the agreement of different actors with regard to the state of your application. And so this is a hairy problem that has been researched for 4 decades roughly. And there's a lot of different degrees of consistency and a lot of different mechanisms for achieving consensus. I'm only going to talk about the 3 sort of most common ones. So strict linearizability is sometimes called single node consistency, also referred to in some areas as serializability. That's a transaction level in JDBC, for example. There's a slight difference between linearizability and serializability that I'm not going to go into, but basically this means that each actor within your system must synchronously acknowledge each write before the system as a whole can progress. And so that yields a total order of operations in your system. That's an extremely expensive thing to do, but it does yield the sort of consistency semantics that we like to believe we're working with intuitionally. When we have multiple nodes manipulating a shared set of data in a database, for example, obviously there is concurrent action happening, but implicitly we like to think that I've programmed this thing to do one thing over here, I've programmed this other actor to do this other thing, and I hope I have some notion, we think we have a notion of when each is going to happen. If you have strict linearizability through a consensus mechanism, then you can enforce that, but it is very expensive and has significant ramifications for the availability of your system. Causal consistency is tracking the temporal relationships among concurrent actions with regard to the dependencies in the data. And again, causality is yet another topic that could be a subject of a full talk. But the basic premise here is that if my change depends on the changes of these three actors, then I need to ensure that that operation takes place after theirs completes. And if you apply this sort of globally across your distributed system, you end up with a partial order of all operations in the system, and that yields nice characteristics like when you write a value to a database and then do a query, you'll be able to see that the effects of that write in the results. When that isn't the case, then you do things like if you have load balancing and your front end writes a value and then another request hits a different load balancer or and therefore a different memcache cluster, you may get a different value out of the read than you just wrote by the other path. So causal consistency would resolve that. And then roughly the weakest notion of consistency is eventual consistency. And that is the one that's sort of been popularized as the default in a lot of the sort of cloud scale data stores that are available from various vendors. And all this means is that concurrent writes made by multiple actors will eventually converge to the same value at all points within your distributed system at some point. And so this is really just a guarantee of what's called liveness in the system, that writes will continue to propagate to all actors that need to be notified of it at some point in the future. And so here you can't really say anything in terms of the orderings of operations in the system from a formal perspective, and that is what yields a lot of the complications when trying to build, for example, a transactional application on top of an eventually consistent data store like now I'm blanking on all of them. Clustered CouchDB, for example. And so the choices made here with regard to consistency will dictate your system's availability characteristics, right? So if you think about it at both edges, if we're working on an eventually consistent distributed system and all actors can concurrently write things and they don't need to wait for anybody, then every actor can remain up. It is not dependent upon any other actor within the system in order to proceed. And so that will ensure that each node can remain up subject to hardware continuing to work. Whereas if you go to the other extreme and you want to achieve strict linearizability, when one actor makes a write, all the other actors cannot accept any new work. And so that means that they are effectively offline with regard to systems that are outside of your control. And so that's what's called availability, and your consistency choices impact that directly. So the point is that you need to be aware of the spectrum of consistency options that you have available to you, and you need to choose the one that most suits your application and your users' expectations and so on. So let's step back for a minute. I'm just going to assume that I've proven my case, that APIs are broken, and that we need something else in order to resolve the complexities that we deal with when building distributed systems. Sort of as passing evidence of that, I'll just note how many tutorials and talks and sort of support mechanisms exist for how to reason about distributed systems at scale, for example. This is because it's very complicated. This means that everyone's architecture is entirely different. The way they built Twitter, for example, is entirely different from the way they built Facebook because they each just sort of made their own ad hoc decisions to address the problems that they hit at each point along the way. And so what I'm interested in is finding a better way to build distributed systems. And in this case, I'm focusing on the difficulties around APIs as sort of the entry point to that question. And so what do we want? Two things. In any application, in any software we write that is distributed, we want to be able to communicate, we want to be able to send data between the various actors within our system, and we want to have computation over that data. Maybe the computation is centralized, maybe it's distributed, maybe it's pushed to the edges. There are all sorts of different possibilities, but these are the two things that we want. Everything else is incidental. And like I said, but I have a lot of experience in programming languages, and I've, to a certain extent, studied the process of evolution in programming languages and abstractions. And we've sort of been down this road before in other domains, right? So 30 years ago, longer, writing software necessitated working with extremely low-level sets of tools like assembly and C. And over the years, people put together better abstractions that yielded more leverage to address the problems that they were faced with when doing programming. And I think really the same sorts of processes need to happen. We can't keep dragging along this notion of we're just going to spit data out a socket in an API and expect to be able to reliably build robust, quality, available distributed systems. And so these predecessors of ours that worked on these higher level languages identified certain problems and constructed these abstractions, and we need to do the same to get above that. And a lot of this work is not so much coming up with a new characterization of how to do this sort of work. It's really about trimming away certain things that we sort of take for granted in terms of our ability to build distributed systems, like spitting any sort of data out a socket that we want and working with that. We need to constrain ourselves in ways that are very similar to high-level languages and how they constrain what we can express in programs, because those things that we're constrained against doing, we found to be well correlated with errors, difficulty in understanding code, et cetera, just as the very primitive tools that we're working with in building distributed systems are very error-prone and very difficult to understand. So thankfully, people have been thinking about the distributed systems problems for not quite, but close to as long as people have been working on programming languages. Ever since networks happened, people became aware of the difficulties around getting computers over here to talk to computers over here and have them agree on things and then compute manipulations over the data that they share. And so every talk has to have an appeal to authority, and this is mine. So in 1978, this is Leslie Lamport. He published a paper called Time Clocks and the Ordering of Events in a Distributed System. And if you read any other material after seeing this talk, I would hope you read that paper of his. And he's not a dumb guy. He invented, in addition to publishing this paper, came up with LaTeX, TLA+, et cetera, and was awarded the Turing Award just last month for his work in distributed systems research. And this paper that he published is really remarkable in that it talks about the difficulties of communication among concurrent distributed actors as essentially a physics problem, which it is. We have time marching forward, and we have concurrent actors doing things, but they need to communicate and coordinate. And so there are certain characteristics of physics and time and the speed of light that constrain what we can do in this problem space. And so read that paper. So that was sort of like the Big Bang in terms of sort of momentum building and people understanding the sort of scope of the problem in the distributed system space. And over the past 40 years, a lot of very sound approaches have been developed, including some very recently. So I'm going to mention two. There are others, but one is called the Calm theorem, consistency as logical monotonicity, and conflict-free replicated data types, CRDTs. The first is out of Berkeley. The other originated in France at INRIA. And what these do, they constrain the types of the operations that your system can perform in order to ensure convergence over time and to eliminate the source of the failures that we experience in distributed systems that are due to those network failure models that we talked about previously. The great thing about this work is that it's not just a sort of novel, clever implementation of something. They really embody and implement formal mathematical models, again, very much in the tradition of Leslie Lamport's work, using mathematics and algebra to provably achieve the sorts of consistency, availability, and consensus guarantees that we want to have in distributed systems, but also simplifying the problem along the way. And I hope I'll be able to explain that as well. So I have two slides that could be characterized as mathy. So this is a bounded joint semilattice. It's an algebraic construct, and what we have here is the flow of time, either logical or temporal, and at each level, there's a operation called the join operation that defines the least upper bound between two concurrent operations. So down here on the bottom, we have this is a set semilattice right here, and so we have the empty set joined with a set containing A that yields the set containing A. The set containing A and the set containing B join together to be the set of A and B. And so the join operation for sets is merge, union. Now semilattices exist for a number of different data types, and as long as you have a join operation that establishes this partial order, so we're always so the null set down there, that's called ground or bottom. And so that's the base value for this type of semilattice. And as you add data into it, you can only add data into it. So your information within the semilattice is always increasing. This is important because given that characteristic, you can have asynchronous concurrent modifications being made to a semilattice like this on different actors, and they can always merge and yield the same value. So you can look at these, you can consider each sort of column here as a different actor within the system, operating concurrently, and then they will always yield the set containing A and B, given the particular operations that are depicted. And the math here is actually really easy. It's like upper level high school algebra stuff. So if your data structure's operations satisfy three properties, it can be characterized as a semilattice. And these are hopefully familiar to you as programmers: associativity, commutativity, and idempotence. These are really useful characteristics in our single node local process programs that allow us to do interesting things in terms of function application and concurrency and parallelism. They apply in much the same way in a distributed sense. And especially because of the commutativity and idempotence, this characteristic immunizes any semilattice data structure from the network-borne faults, including reordering, multiple delivery, and loss of messages, as long as liveness is preserved. That means that if a message was dropped on the floor, that your nodes will know to retransmit at some future point. And so your system globally will continue to progress upward in that semilattice as, for example, eventual consistency carries on. So getting away from the math a little bit and back towards programming, data models are everything in what we do. And I was talking before about how some of the solutions that our forebears in programming languages came up with constrained what we could do within our programming. But the great thing about semilattices within distributed systems is that they actually expand the set of data structures and set of operations that you can use within a distributed context. There are known, implemented, and formally proven semilattice data structures for counters, registers, sets, graphs, trees, multi-maps, on and on and on. And so if you have a distributed data structure that all the actors within your system can be manipulating without running afoul of the types of network failures that we talked about, and still use data structures that are as rich as this, that is far and away better than what we have right now, where we're simply pushing very impoverished representations of our application's data from one point to another. So I come from a closure background, as I said before, and so immutability is very important to me, both in terms of programming practice and the sort of formal benefits it yields to my programs in terms of simplicity and robustness. And the great thing about semilattices in this dimension is that immutability meshes perfectly well with the model. So when I said before that the semilattice only accumulates information, that should sound exactly like the persistent data structures that we are used to today, where there's a great deal of sharing of information, and it corresponds perfectly well with things like immutable logs, which is a foundational piece of a lot of the distributed systems architectures that are already in use today. And so once you have, if you have a semilattice data structure where the components of it, the entries in a map, the values in a set, etc., are actually immutable values themselves, then for free, you get all the benefits in a distributed context that you do from immutability in a single-threaded or multi-threaded single-process programming context using immutable data structures. Histories, rollbacks, undo, consistent snapshots all come for free. This is, I think, sort of an earth-shattering consequence of meshing the formal characteristics of semilattices and the advantages that I'm familiar with, and I hope you are too, of immutable data structures. And so in terms of what this says about APIs, getting back to our original sort of point of leverage here, what does an API look like in this world where you have a shared semilattice data structure that all of the actors within your distributed system are collaborating around at the same time? Well, you can reify, again, for that more request-response type of coordination model, you can reify operations into data. So instead of calling some method on an API stub or calling through a HTTP gateway, you create a bit of data that represents exactly the same operation that you wanted to apply previously, But because it's data and it fits within the context of this shared concurrent semilattice data structure, it has the same effect, but yields none of the downsides of the API model that we talked about previously, and provides all the benefits of the immutable data structure and semilattice semantics that it has. And something that comes along for free as well is that quote-unquote operations are computable. You can do things with them. Whereas API calls, they're sort of, as I said, they're implicitly imperative. So you can't easily intercept an API call. You can't easily reroute it. You can't distribute it to multiple peers in order to run a computation in a sort of scatter-gather architecture, for example. Once your operations are data, you can route them, you can copy them, you can distribute them, you can replay them at any level in your system, not just in the back end, in the front end, in caching tiers, and on and on. And you can see this if you use queues heavily, right? Because queues don't have an API. There's not that coupling in queues that you have with APIs, where you know who the consumer is on the other side of this queue that's going to pick the message up. So you need to encode this operation into data, put it on a queue, and off it goes on its way. And so if you work with queues a lot, then you're very familiar with this tension between a coupled binding between a caller and a callee versus the uncoupling that exists between a producer and a consumer with a queue in the middle that only has data going back and forth. So that's the data side of things. The programming models around semilattice data structures is less well fleshed out. And I think that's a little bit of a good thing, just because we want to have a sort of well-founded solution to our distributed systems problems, but we don't want to throw the baby out with the bathwater. And so there's a lot of different programming models that you can apply within this context. So event sourcing and other log-structured approaches mirror and match up very well with what I've been talking about here, as well as stream-based computation. So if you are replicating values that represent the operations you're performing over your data, you can use Storm or any other of the stream computation platforms to do that routing, the duplication, the scatter gather, whatever architectures you're interested in, you can apply the stream-based computation primitives that are available right now. One thing that I'm particularly interested in, and what I've been working on most heavily in this in the programming model side of things, are things called tuple spaces, which is a subset of what were originally called blackboard systems. And when these were originally contemplated, they were thought of as sort of mutable global bags of state, where you would have computational services and agents would come in, ask for data that matched a particular set of criteria within the tuple space, and it could remove it, do some work, and then put back a result. And so the metaphor is this blackboard where there's multiple agents collaborating over this shared resource. Tuple spaces and blackboard systems, when they were developed in the 70s and 80s, were all sort of implicitly imperative, not using immutable data structures. But I think that model, when applied to semilattice data structures, has a lot of traction. And so the primary implementation of tuple spaces was something called Lynda. That's the programming language. There actually are implementations of Lynda for lots of modern programming languages as a library. And so it's interesting to play around with and get a sense of the semantics for it. And really what this is if you combine the immutable set of semilattices that you might have available with this notion of waiting for values in this shared distributed data set to match on queries or criteria, you can establish the same sort of reactive patterns of computation that you might have within like FRP systems. And it's very much like what happens in database systems with triggers, for example. So you have a trigger that is fired only when data that matches a particular query comes along. And so it's very much a corollary to the sort of model that I'm talking about here. Again, you can have RPC-style systems interacting with a system like this as well, but again, it's more of an interoperability question as opposed to it being a full peer within the system. So you want to do the same sort of transformation that I showed previously about getting away from an imperative operation and using whatever RPC-style system that you're exposing or having to consume, bring that into data as rapidly as possible so that you can apply have the same sorts of benefits with that data coming in. And then there are actually a couple of totally new programming languages that assume the semantics of semilattice data structures. And the most well fleshed out is one called Bloom. That's again out of Berkeley. And it's a Ruby DSL actually, where all the data structures are semilattices. And they call it a programming language for disorderly computation. And what that means is that all of the expressions in your program have no predefined ordering. It's not, the expression on line 1 runs at time t, and the next line runs at time t2. They all run concurrently, and because of the nature of semilattices and their ability to accommodate concurrent actions by multiple actors, the state of that program will yield the same end result as a sequential program, but can be integrated into a broader distributed system, all with the same set of semantics. It's an incredibly ambitious approach, but again, one that requires a new language, something that I'm personally not a fan of, given the difficulties around changing languages like that. So just to review, what do we want? Communication and computation. And I know there's been few specifics here. Part of that is because what I've been working on is still in progress, but also because all the concepts here are that new that everybody is sort of everybody who's interested in this area is working towards a practical system that sort of embodies all the principles here. But the end result, at least from my perspective, is to have a system where stateful services are manipulating a shared substrate of data reactively. What that does is it supersets all of the use cases that we explored earlier with APIs. There's no coordination required among concurrent actors within this sort of system, and it allows for arbitrary computational models and topologies, both in terms of the network and your broader distributed system. So I referred to a lot of prior art. Listing them all would require many, many slides. You can actually get most of them via Chris Micklejohn's reading list there. If you're interested in these sorts of topics, do go read everything if you can. There's actually not a lot of material, and again, the math is very tractable. Again, there's Bloom, which is the language that is implementing disorderly programming using semilattices as the foundational building block for all of its data abstractions. And then my project is called Quilt. It's, as I said, in progress, but getting near releasing things shortly. And I'd be happy to take any questions.
Is what you're working on a set of macros like core async for closure, or is it something totally standalone?
So the question is whether Quilt is a set of macros like core async or something standalone. It's not just a set of macros. It is in part an observed remove set CRDT. I mentioned CRDTs as one of the characterizations of semilattice data structures that can support, as I said, sets, graphs, maps, multi-maps, counters, et cetera, sort of as that base substrate of data. And so now I'm working on how does that best fit into the programming model that I like, which is closure and such. So what it's going to look like sort of concretely in Clojure in particular is exactly what I'm working on right now. But what I'm aiming for is for Quilt to be totally language agnostic. It's not going to be tied to Clojure in any way whatsoever. The reference implementation is in Clojure because that's what I appreciate, but hopefully it will be compelling enough for people to pick up and run with it with other languages.
Thanks a lot for the microphone. And thanks for the talk. It was very, very nice to see this laid out like that. We're using CRDTs, for example, to great effect in Akka, and are benefiting greatly from how they work. I just wanted to point out that there are several different kinds of conflict-free replicated data types, and the semilattices you show have the tendency to grow. Well, you only add information, and you can't really remove any ever. So if you have a use case where that is a problem, there are others, like the commutative replicated data types, just to give a hint to people if they run into issues with that. Another thing I wanted to mention is that any kind of coordination you do has a cost. And for example, if you run an Akka cluster, it does the exact same thing with this semilattice, and we ran it with 2,500 nodes. But the gossip dissemination and the merging of all the things and so on all takes longer all the time. So as soon as you introduce coordination, you cannot scale infinitely anymore. So you should also be clear about that. That it's not a golden hammer. You need to keep things at a reasonable scale for the consistent part, even if it's only eventually consistent, because even that has a cost.
Yeah. So just those are all good points. And so a couple things I would say is what the gentleman mentioned about the size of the semilattices growing without bound. That is sort of the baseline that we're at right now. There's ongoing research about how to do effectively garbage collection within CRDTs and semilattices that will hopefully resolve that issue. There's also the notion of being able to prune your data set without necessarily impacting its semantics going forward. So basically taking a checkpoint and then saying, I want to discard history going backwards. There's various ways to do that. And one thing I forgot to mention, since we have someone in the audience that's actually using CRDTs in production, is that there are people using these sorts of technologies or principles in production. Very often they're implemented in-house to address sort of pressing distributed systems needs. But the people at Basho who produce the React database, their upcoming version 2.0 includes CRDTs as a data type within the database. So you have CRDTs implemented in your database that multiple clients can connect to and manipulate in exactly the way I was talking about here, although they don't. They're a database vendor, so they don't talk much about the programming model. But that's a great option to look into if you're interested in playing around with sort of production-ready CRDTs, is to check out React and their new data types in version 2. Yeah.
Great talk. You mentioned something about how everything should be a stateless service. I'm sure I'm missing something here, but let's take a very primitive example. I want to give you $1,000. $1,000 should go from my bank account first, and then it should land in your account. That can be stateless.
Yeah. So that last, I should have been very clear. The third bullet point there in this slide is my characterization of the problem and what I'm pushing towards with Quilt, which is going to be useful for many things. Probably not for banking transactions to start, just because that's not the set of use cases that I'm interested in. You can absolutely have different types of programming models that work with CRDTs, and so you can have an application that maintains the transactional characteristics of the things that it needs to be transactional with over here. using whatever consensus and consistency mechanisms that you're using already. And the results of that can still feed into, for example, a CRDT that you use to drive your website. And so you don't need to use this as the one data platform that's running your entire business, for example.
It doesn't have to be only banking. It can be even simple thing like a shopping cart. I'm on Amazon, I'm picking up this item, dropping this item, let's say I don't want one banana, I want 2 bananas. Even that has state.
So in that case, it's not the service that has the state. The state is in your cart, which is stored within their eventually consistent data store. And so the Amazon cart is actually a great example of eventual consistency being applied in a stateless way to a user experience where transactionality actually isn't used at all. Any other questions? Yeah.
So some past experience with algebraic data types has shown that you're generally in for a world of hurt if it turns out you define something which doesn't actually meet the axioms. So if I thought something was a semilattice, it turns out months later I was wrong. Do you have any thoughts on how programmers can be helped to define things that do meet the required axioms?
Yeah, so there's one thing is to not implement anything that defines the axioms at all, right? So if you have someone that has implemented CRDTs already, then the operations over those data types will be defined and hopefully quality checked appropriately. There are actually a number of different efforts ongoing to use various theorem provers to ensure that the axiomatic invariance of associativity, commutativity, and idempotent apply to the set of operations that you're defining on the CRDT that you're implementing. And then again, all of the same sorts of quality assurance issues around software apply to this just as well as anything else. So things like property-based testing, typing if you have it, all of those things can be helpful. Any other questions? I think I can do probably one more. Thank you very much. I appreciate it.